So now we are moving to the second talk, and so we will again go in just in 5 countries in Europe, and looking again at mortality and health. So Konstantinos, please.
Thank you. The discussion is about mortality and health in 5 countries of the Eurozone area. We're talking about Greece, Ireland, Portugal, Spain, and Italy. These are the peaks, but we don't like this term, so we do not use it. Well, what we will have, and I will give an introduction to the first Einstein theory and all the other things. Probably I will spend more time in method, in describing the method than the results, but you will see. Well, what about mortality? Everybody knows about mortality, everybody knows about life tables, and the question is, can life tables describe the health of the population, the health status of the population? Well, the answer is no. If we define health in a broader way, as who the World Health Organization did in 1948, as a state of complete physical, mental, and social well-being. So, what can we do? In the 60s mainly, there were some efforts to analyze health status. The first one was of Sanders, which used the effective life years as a measure of the current health of the population based on mortality and morbidity rates. The second one was of Chania, which introduced the term index of health based on the probability distribution and the number of and the duration of illness and the time lost due to death based on data from the Canadian Social Sickness Survey. Actually, sorry, what happened here? Okay, there is the famous method of Sullivan, which calculated 2 indices: the expectation of life free of disability and the expectation of disability. What he did, he used data, he used averaged life tables and surveys conducted by the National Center of Health Statistics. Actually, he was of the first that he did join the 2 methods, life table analysis and surveys, in a more effective way. And that's why the World Health Organization currently is using this method for the estimation of healthy life expectancy. Well, the next important is of Thrace. Thrace supposed this: we have the health status of a population. And a person could have a health status of 0, which means that he is dead, and the health status of 1, which means that he will have the best health. The health status of the population can change all the time, in more or less stochastic way. However, what can we do? We can find the health status of a person throughout his lifetime and average all the estimations in order to find the health status of the population. Does it work? No. It doesn't work because it's impossible to find the health status of a population by averaging, simply because we don't know the health state of a population each time in his life. So, what can we do? The idea is, quite briefly, this. The health state and the vitality of an organism can be estimated from the life table, and simply from that, without the need of any additional data. What is the health of an individual? Nobody knows. It's a stochastic process, and death comes when? When a person's health falls below a lower limit. Nobody else can estimate it before. That way, the health state is the opposite of mortality, and the health status function is the opposite of the mortality function. This is the idea. We can find the mathematical solution of this idea in these papers, for example, in 2010, 2013, 2014, but we can describe the health status of a population like this. Here is the health of an individual. You see, the health is going, the health, oh, not the health, the health, the health. The health is going that way, and a person dies when his health becomes zero. Another person and another person. What can we do? We can average the health status of each individual and find the health status of the population. But how we can do that? Well, in these papers that I presented to you before, it was found, it can be proven, that the JX distribution, what is the JX distribution? The DX distribution divided by the radius of the line table, and the health of the population, the health status of the population are connected like this. And the health of the population can be estimated with this formula, where K, A1, A, B, L, and C are unknown factors. We don't know anything about them. So we need to estimate. Before that, we can see that the health status is increasing at the time point, which corresponds to the health, to the maximum health state, that is around age 40 more or less. And then health decreases in order to be zero at a very late age. How we can do that? The first thing, the first thing is how to do the calculation. So what you need is a very sophisticated Excel sheet and very difficult Excel sheet. But Professor Skiadas has prepared many things, has done many things about it. So what we need actually to do, we just add the data about births and deaths in a population per age. The second thing that we need, that we have to do is to normalize the JX distribution, because we have different populations and we have to compare them, and then we have to solve this equation in order to minimize the sum of square errors. If we minimize the sum of square errors, changing the values of the parameters, we can estimate these parameters. We did that. As you can see here, no, you cannot see it. You cannot see very well. As you can see here, this is the original fit, the green one. But you see here, we have some deviations because of the excess of mortality between the ages of 15 and 30. You see, there we know that we have some problems with data. So we had to fix this. What we did was to add to our model two serrative Goebbels factions. And then, after we add these Goebbels factions for the ages 15 to 30, we solve again the equation. The result is this. We took a coefficient of determination that was perfect. And in some cases, okay, it was not that perfect, but it was 0.998 or 0.999. Okay. What we can do then? How can we use this method? In our point of view, the first application is quite obvious, as you can describe the health status of the population. The second option is to be used like a fitting method. Here you can see the death curve, and here with the magenta color you can see the final fit. It's almost perfect. And okay, so what did we do based on that methodology? We did measure the life expectancy at birth, the life expectancy at age 65, and several other indicators like the modal age at death, the median age at death, and several percentiles, the 10th, the 9th percentile, the 25th percentile, and the 75th percentile, and the range within these percentiles. Well, the next thing, we thought, okay, we have here a line. Can we describe the width in this part of the mortality curve? So we did this. We calculated, first of all, the speed of change of the mortality rates. How we estimated the speed of change of the mortality rate? We just subtracted one value from each previous. And we found that here we have the maximum speed of the death rates, which means that here we have the health status of the population, or the mortality of the population, is burdened rapidly. You see, this was called the left inflection point, and it corresponds to one point in this distribution, the DX distribution. The next thing that we did was to estimate the acceleration of the death speed. How do we measure the acceleration of the speed? In the same way that we measure the speed change of the mortality rate, we just subtract two successive values. What we found was that before the left inflection point, the acceleration of death rates became maximum. Afterwards, it declined, and at the left inflection point, the acceleration of the death rate was 0. Afterwards, the acceleration followed that reversed bathtub order, okay. And then, if you can see here, because of the changes in the acceleration, when the acceleration is again 0, we have the minimum change of the speed rate, of the speed change of the mortality rates. This was the right inflection point. So, we had calculated a point where the speed rate was maximum, and a point where the speed rate was minimum. The difference, the edge distance between these points would give the width of the mortality curve. The next thing that we had to do is to measure the health indicators. We can measure several things here. For example, we can measure this point. We can use this point. This point is the point at maximum health, where the curvature of the health state reaches its maximum point. The second one is that we can measure the length of this line, which represents the total health state of the population. We can find a point where health is 0. We can and several other measures like the expected healthy age, the total life expectancy without any serious or moderate diseases, and so on. I will give you a quite... No? No? Don't have time? 5 minutes? Less, okay. Okay, less. We use the data from the human mortality database and the Eurostat database. Actually, the two databases are more the same, similar. Okay. Here we see life expectancy at birth. We see the convergence trend, but you see we have at the end enough variability among the population studied. The same is for females, but there you can see that Italy and Spain are clearly distinguishable. The same is, okay, you can make several observations about the E65 and class 65, the median age at death, and so on. What I want to show is the left is the model age at death and the death density at the model age. The model age at death is this. You see here the fitted line. So what we need is to have an estimation of the age in which model age at death is achieved and the height of the curvature. What we have to see is that the convergent trend is more clear. But concerning the height of the curvature, there is a great difference in Greece. Greece is here. What is happening in Greece is that the line is moving towards older ages, but at the same time, its height remains the same. While in the other countries, this line moved towards older ages with changes in the height of the line, in the height of the Jakes distribution. And I'm gonna finish with the left and right inflection points. Here is the right inflection point. Here is the left inflection point. The distance between the two inflection points gives a measure of the width of this part of the line. What you can see is, first of all, by comparing the two sexes, these are the males, these are the females, and these are the males, you can see that the gap is narrower in females. Why is that? Because probably mortality transition has moved ahead in a more efficient way there. The second thing is that if you compare this with this, the right inflection point with the left inflection point, what you can see is that here this point moves more, let's say, moves fast, quite fast in comparison with this point. As a result, by time, the gap between the left and right inflection point becomes narrower, so the form of this line becomes narrower too. Okay, I can skip the 15 and 25 percentile in order to give some, and I didn't have the time to discuss about the effects of economic crisis. But we can see the effect of economic crisis here. Here is the total health state of the population. If you see, we have an improvement almost everywhere except Greece. This is, of course, the result of the economic crisis.
And this is Greece?
Yes, this is Greece.
Okay.
We are a paradigm of peculiarity.
Yes.
The next thing is that we can see this point. You will see here in Greece, this point does not change much, but not in the other countries where the differences are bigger. And we can see the expected healthy age, that it goes upwards in all the countries, except Greece in the last 2 years. But in all the other countries, you can find paradigms where the improvements are either halted in the last 2 or 3 years of the study, or either the health status decreased. I don't know what will happen after the economic default of Greece, but we will see. Well, sorry to be torturing you. Thank you very much.
We have time for 1 or 2 very short questions.
No questions.
Perhaps I can give you an explanation in one point. Because if you see this diagram there, it's, if you see there is the health status of the population, and if you count all the area, not the dark part, the other part, you count this area, with this area you can find a sort of measure of the total health state or status. That is interesting is that if you count this total health status, which is an area, and it's very easy to calculate, after you found that it's in very close connection with health, with some health indicators, and also is in some close connection with the way we measure the life expectancy at birth. There are some differences, but not many differences. And also, if you find this curve for men and women, in all the cases, women is higher than men, so it's compatible with the theories that we know until now. And so after, if you see also this area and also the dust part of area, we do the following. We divide the one part with the dust part, and it was a surprise for us that by dividing these parts, we have exactly the numbers close to the numbers that they estimate from the World Health Organization about the disability years. And so we are working on this because it was quite interesting why we are so close to the World Organization. But I think in the other presentation there are some things about that. So thank you.